Is your AI agent secretly hiding something? Welcome to The Hidden Layer, Decoding Artificial Intelligence. Today we're unpacking a groundbreaking explainer on building highly verifiable, production-ready AI agents. More importantly, we're going to show you exactly how to apply this research in the real world to secure your systems.
Imagine this for a second. Your AI agent is secretly exfiltrating your workspace data, or quietly elevating its own privileges, and you literally can't stop it. Why? Because its underlying code is just this unreadable, massive wall of text. In the current landscape of autonomous systems, if you don't know exactly what your agent is doing under the hood, you are flying completely blind.
We're going to solve this exact problem today by introducing the SSL representation. It's a brilliant method to transform those text-heavy AI skills into strictly structured data. And hey, I want you to stick around until the end because I'll reveal the incredibly counterintuitive reason why upgrading to this advanced structured data means you should never actually delete your original clunky markdown files. It's a twist that will totally change how you manage your repos.
Section 1. The AI Agent Blind Spot.
So let's dive into the massive blind spot that's currently plaguing applied AI engineers. We're building these incredible autonomous systems, but our foundation is, well, surprisingly fragile. Look at human reading. Writing a standard SKILL.md file in natural language is incredibly easy for us developers. It's expressive, it's readable, and it tells a story. But for automated systems, it's an absolute nightmare. While natural language is great for us, it forces automated routing and security systems to infer really complex properties from noisy, incomplete text, and that creates a massive representational bottleneck.
Just think about what happens when you look at a standard skill file. You are completely tangled in the text. You've got invocation instructions, control flows, loops, execution constraints, tool calls, and sensitive resource usage, all just messily entangled together in these sprawling paragraphs of prose. If you're an engineer trying to build a secure, verifiable system, you absolutely cannot rely on an LLM to parse these paragraphs reliably every single time without hallucinating or worse, missing a critical security flaw.
Section 2. Enter the SSL representation.
To solve this text entanglement, researchers introduce a really brilliant architectural shift known as the SSL representation. The crucial point here is that SSL acts as a source-grounded normalizer. It takes that unstructured, messy text and maps it into a tightly typed three-layer JSON graph. What's absolutely fascinating is that this is actually based on classical linguistic knowledge theories. It literally takes the chaos of human language and forces it into a predictable structure so machines can actually understand what the skill does, safely and reliably.
It breaks a single-agent skill down into 3 digestible layers. First, you have the scheduling layer, which dictates exactly when the skill should be invoked. Second, the structural layer, which defines how its work is organized into distinct phases. And third, the logical layer, which pinpoints exactly what atomic actions and resources it will touch.
Section 3. Layer 1. The invocation interface. Let's see how this builds a rock-solid foundation for skill routing. Say you have a registry of 10,000 skills. This is how your agent finds the right one instantly. Instead of unfolding the full, massive execution code just to figure out what a skill does, this scheduling layer exposes a stable, capability-facing contract. You get the skill goal, the intent signature, expected inputs and outputs, and crucial dependencies. You know exactly what to expect before any deeper inspection is required. It's kind of like reading the back of a book instead of reading the whole novel just to find out the genre.
Section 4. Structure and logic layers. Now we zoom in to see exactly how the AI agent actually executes its tasks out in the real world. This brings us to the structural layer. This layer organizes operations into stereotyped activities, or ordered scenes. Instead of a chaotic block of instructions, the agent moves gracefully through a highly predictable timeline. Stage 1 is prepare, where it validates the input. Stage 2 is acquire, loading the necessary data. Stage 3 is reason, applying logic. Stage 4 is act, which is the execution. And Stage 5 is verify, checking the results. It makes multi-step workflows entirely inspectable.
Now, underneath those broader scenes is the logical layer. And honestly, this is where the magic happens for engineers. The logic step is the smallest operational unit the source artifact supports. It breaks down the execution into atomic actions without inventing or hallucinating any missing implementation details. It strictly, literally represents what is actually written in the code.
And this brilliantly illustrates how the system achieves true standardization. It uses closed vocabulary actions: read, write, call tool, update state, terminate. By using a closed, rigidly restricted vocabulary for primitive actions, it makes the entire system verifiable and comparable across thousands of different skills. You don't have to guess if the word fetch means the exact same thing as download. It is all mapped to strict, understandable primitives.
The exact same rigorous logic applies to bounded resource scopes. By explicitly defining the resource scopes, whether the agent is touching memory, the local file system, the codebase, credentials, or the network, engineers can see exactly where the agent is allowed to operate. This effectively locks down critical boundaries. If an agent that is supposed to only read memory suddenly has a network scope, you instantly know something is wrong. Section 5. Real-world skill discovery. These layers translate from academic theory into solving massive real-world headaches. When researchers tested this within the AI-GNA framework on a huge corpus of over 6,000 skills, utilizing a rich SSL-derived description bumped the discovery accuracy, measured in mean reciprocal rank, from a baseline of 0.573 all the way up to 0.707. Recall at 10 also jumped to nearly 90%. That is a massive operational leap in reliably matching a user's request to the correct executable skill. What you should really take away from this is a fundamental principle of AI engineering. Concise, structured summaries are far more effective interfaces than simply embedding longer source documents. Stripping away the noisy prose and leaving only the pure, structured interface signals makes routing the right skill significantly easier for your system. Simply put, more text does not mean better context for a machine.
Section 6. Verifiable agents and security.
As an applied engineer, the most critical part of your job isn't just making things fast, it's catching threats before they happen. You really have to treat risk assessment like a high-stakes cybersecurity thriller. We're talking about catching data exfiltration, destructive behaviors, privilege escalation, and covert execution. When an agent suddenly requests credential access or initiates some destructive network behavior, and it's buried in a giant paragraph of Markdown, a standard reviewer might easily miss it. But because SSL forces typed operations and explicit resource scopes, it flags these threats instantly.
And the data confirms this beautifully. Looking at the macro F1 risk assessment scores, relying purely on the full SKILL.md text gets a score of 0.744. But the data clearly shows that combining the original text with the SSL representation achieves the highest overall risk detection score of 0.787. You absolutely get the highest fidelity of risk detection when you use structured evidence.
As the researchers explicitly state, SSL is best understood as a practical step toward more inspectable, reusable, and operationally actionable skill representations, rather than as a finished standard. They readily acknowledge it isn't a magic silver bullet that solves all security woes forever, but rather the essential missing manifest layer you absolutely need to inspect your agents properly.
And this brings us back to our secret from the very beginning, the open loop payoff. You must never delete your SSK.md files. Why? Because SSL is an evidence interface, not a replacement. The structured SSL acts like an incredibly precise alarm system, pointing out the exact mechanical risks, like an unexpected API call. But the human-written source text supplies the critical context needed to interpret why that call is being made. You need the structure for the machine to flag the risk and the prose for the human to interpret the intent. Together, they are the ultimate dual-layer defense.
So, the ultimate question is, how will you secure your next autonomous AI agent? Now that you understand the immense power of structuring your agent skills with SSL, we want to know what you plan to build next. Let us know down in the comments, and don't forget to subscribe to The Hidden Layer to keep decoding the future of AI. See you in the next explainer.